is a web service, so users can actually see building and room access history. On the left is showing the completed module blocks, and on the right is showing the internal components contained within the house.
So in this video, it shows our working prototype. Marina first uses a card without access to the database. As you can see, the door will not unlock. Now she'll use one with access to the database, and it'll allow her to open the door and walk through.
Alright, and this is just a simple flow diagram of how the mechanism is actually working. So when you tap the card, it's going to interface with inductive labeling, and then through a serial peripheral connection, it'll go in through the Raspberry Pi, which will then verify whether or not it'll work. If it does work, it'll send a request to the web service where from the database it'll track the data, and then it'll go through to the bottom part, which is the circuit unlocking.
Now for ethical considerations, since this uses near field technology, which operates on a wavelength of 13.56 megahertz, we need to make sure that people with pacemakers know the possible dangers with the radio frequency that it's at. Also, we also need to consider that since we are using our own database, that the user's information is not shared with any external entities and it's secure.
So some constraints for this project, like get rid of project. We are having this project must be due by today, April 26, 2025, and our budget is $500.
Now for requirements, for the mechanical side, we needed to make a housing that would hold all the electrical components, which is about 7 pounds in weight. And then it also needs to be relatively close to the door, about 24 inches.
On the electrical end, we need to supply 12 volts to the magnetic lock. This will create a lock on the door, and then we need to have 5 volts and 2.5 amps. This is critical for the Raspberry Pi to supply the module. And lastly, we need to have access status display, which we use our red and green LEDs.
Alright, and going into the software portion, we needed the module to be able to interface with the web service. With this, we needed to have a database and it have the ability to store data. And then after that, we needed to have administrator access where they can manage the users and also see the access history. And then for the user access, they needed to be able to view the history that their own personal history for it.
So for mechanical specifications, we made our box 5.5 inches all around. We made the wall thickness about 0.2 inches thick to make sure that it could withstand all of the weight from the electrical components. It is 3D printed in ASA material. It is UV stabilized to make sure that it's fine outside. And then we also use security fasteners to make sure that no one can tamper with any of our electrical components and cause any issues.
For the electrical end, to achieve supply to the magnetic lock and the NFC module, we're going to be using 2 power sources. One will supply the magnetic lock via a center cut transformer connected to a bridge rectifier, and then we'll connect that to a buck converter. And then for the Raspberry Pi, we're going to be connecting that directly to power that directly by a power cord that will supply 5 volts and 2.5 amps. And then the NFC module itself, that's consisting of the Raspberry Pi, the NFC reader, the relay, and the LEDs. And all the electrical components must fit on a 2x4 inch PCB board due to the size constrictions of the housing.
Alright, for the computer module itself, we decided to go with Raspberry Pi 4B, and then we decided to use MariaDB as the database for this, which is a drop-in MySQL replacement. And then we use an Apache web service, where on that web service, we would be able to differentiate between an administrator and users.
supplied by the one power source, which was the center tap transformer. Each tap will supply the NFC module, and another tap will supply the magnetic lock. So this is the initial schematic built on a breadboard, and then later on a PCB. So some good things about this is we received the correct output voltage for both the lock and the NFC module, but some issues were that the output current coming to the NFC module was not enough, so we needed to revise our schematic.
All right, this is the initial software page. There was a lot of issues initially when I started off with this entire project. A lot of issues with using the database and a lot of issues in general with making it work with the web page. This actually didn't work at the time because I was having a lot of issues with it, but this is just the initial part.
This is our current working prototype. The first video is Dustin being able to get into the door. As you can see, the LED will light up. And here's Dustin not being able to get into the door as it's off. It's a little harder to see, but the LED is still on. We also did it through my wallet so that you can show that it's a lot more convenient for users. You don't have to physically take out your card. It'll just go to your wallet or however you want to do it.
This does come with a caveat though, because if you have an RFID protected wallet, it will not work because it already blocks the material.
Okay, so for testing mechanically, we started with radiation testing. We wanted to make sure that the housing would be able to stay outside in case we put it outside. So we did 3 different temperatures. The highest temperature went up to 113 degrees Fahrenheit, and we got a peak irradiance value of about 3, which is not too much to worry about. And then we went on to temperature testing. We wanted to make sure that the transformer did not give up too much heat and cause any warping or issues with the housing sides. So we measured the temperature of the transformer and the size over time. So here's with the result of the lock on. So obviously the transformer temperature is going up rapidly, and then the surrounding walls are also going up, but not as rapidly. This was over a 15-minute period. This is what we determined was the best because it sort of leveled out temperature-wise after this. But the walls were not warping, and there was no temperature difference, and it did not seem to cause any issues. And then we also tested it with the lock turning off. This was only happening at 10-second periods when the transformer is off. As you can see that the transformer temperature goes down to follow the walls. Again, nothing to worry about, and this was over a 5-minute period. So we also did some calculations for conduction. At the highest temperature difference, we got a value of about 0.0176 watts, and then we did it again for the lowest reported temperature difference, and we got about 0.004 watts, and then here's the sample calculation at the bottom to show you how we got those values. We also did some strain gauge testing to make sure that the weights of the electrical components did not cause any issues on the housing. So we had the module tested without the transformer in it and then with the transformer in it. And the results that we got with the transformer being put back on it was a load module value of about 86 microstrain, which again is very small and should not cause any issues or any deformations.
So now we're going into the simulations. This is the model that was simulated in SolidWorks. The lower right-hand compartment is where the transformer is. That's about 4 pounds. And then on the left side is where the PCB, our next heaviest item, which is about just under a little bit of 3 pounds. And in the back is the mounting plate that's going to be fixed on the wall. Now first is the strain. We obtained a strain of about 53 microstrain. And this is because it's an ideal case. This does not take into consideration the imperfections when 3D printing or the dividers that have a tight fit in the main component. This is the shear stress. It's about 7.6 psi. This is located where the transformer is. And then the displacement, again, this is more fixated around where the PCB and the transformer is. And we got a max displacement about 2 times 10 to the negative 4th of an inch.
So this is the revised electrical schematic. So like I said before, we weren't able to do the single power source, so we moved to 2. The one will supply the magnetic lock via the transformer, rectifier, and buck converter. And the other one, which will be just the power cord supplying the Raspberry Pi, and I'll supply the reader, the Pi itself, LEDs, and it'll be able to send a signal to the relay to turn on and off the lock. These are some calculations relating to the magnetic clock section of the circuit relating to voltage, current, and power. So this is some initial testing we did. On the left is showing the transformer. We tested the transformer with the bridge rectifier system, seeing if that's functioning properly. On the right is showing the initial circuit again, but we're testing the buck converter, seeing if the output voltage is correct and what we need. On the left is showing relay testing. So we connected the Raspberry Pi to the relay and tested to see if the Pi would output the correct signal. If it did, the relay would engage and then the magnetic clock would disengage so you can open the door. If not, the magnetic clock should stay engaged. On the right is showing the functioning red and green LEDs. On the left is showing the system testing of the magnetic clock system. So on the top you see the NFC reader. A valid card is tapped. That'll send the signal to the Raspberry Pi. The Raspberry Pi will send a low signal to the relay, telling that to disengage the magnetic clock. If an invalid card has touched the reader, the magnetic clock will stay engaged. And on the right is showing the system testing. This is the NFC module and the magnetic clock and LEDs to test if it's all functioning in unison together properly.
All right, now segueing into the software, it is connected to the NFC reader through a serial peripheral interface. This is recommended by the manufacturer of the NFC board. And then this is just a general flow chart of how the system is working. So what happens is when the card is tapped, it's going to connect to your database as well as that's on both the Pi and the web server. And then it will distinct between two different logins. So it'll have an administrator login and a user login. You can add, view, or edit, and then user login, you'll just be able to view your access history. Going into the next slide. These are the parameters I use for the database. What links them all together is actually the Wilkes identification number that is given to every student when it enters here. So you'd have to use your own. And then this is just the login screen. And then going into this is just the manage users. It's distinct between who is logged in. So if you are an admin, you would be able to view this. And then for the next one, this is just the manage users where you have the actions and options to do it. And then this is just another add user, which is really the intended purpose of that section. And this is the user dashboard. So they will only be able to view their own personal access history. They cannot view anyone else's, just their own. And then you'll be able to log out. And this is just a quick video demonstrating what everything is doing. So as you can see, it's just you type in your username and password and it'll try to verify it. And then it's just showing the distinctions between the different logins.
So here's the first part of our work breakdown structure. It's how we broke down our work mechanically and this electrically. And then here's how we broke down software testing and management-wise. And then here's our spring 2025 schedule. We did not add the fall in, but this is about when everything was due, when we started it, and then all the topics that were due. And then here's just a graphical view of it.
All right, so for the budget, it costs us a total of $415.98, which leaves about $84.02 remaining for that. And then for our real world cost, and I'd like to thank facilities for donating us a door, it brought it down considerably, it would be $544. And then going into the future improvements, there's a lot that I would like to do. I would want to be able to add to the wallet and also distinct between the separation for more security. I would also want to make it be able to run on one power source so it would be able to, so it just simplifies the operation. And then I would like to just improve the navigation and add more functions to it.
As a conclusion, we face many issues, so that led to many design changes, but at the end of the day, we have a complete and working product.
Here's all of our acknowledgements. Thank you to everyone who helped us during this project. All right, any questions?
You have a 5-day power supply supplying something like
Yes, that's the power cord.
Where the heck does that 3 amperes go? I mean, that's a lot of,
Yeah,
that's a lot of current. That can't be just your raspberry
That is
Pi.
the initial required current to start up the Raspberry Pi. That's what it needs to boot up all of its functions. It is like defined in the spreadsheet of the Raspberry Pi.
So you're saying that you don't draw an average of 3 amperes? So do you know what the average is? Do you have a quantified? The point I'm getting at is that's a monster of a transformer that you've got inside that box. And I have a feeling you're using less than 10% of its capability. And that's 4 pounds in your cabinet and a lot of extra electromagnetic potential interference for your computer rattling around inside.
We did measure the interference, that's what we brought the Faraday fabric. It does not affect the system.
Getting back to the power supply, can you put the power supply there? Okay, there. So you've got your 25 volt center transformer, you're only using half of it. And you've got what amounts to a half-wave rectifier because there's some problems in your schematic there, I believe you'll find. And you go into a buck converter, but that converter is only providing a momentary load to your solenoids, right?
No, it's constant.
I mean, it's supplying that constantly, but you're not drawing that power except when you activate the solenoids, right? Point is, you've got a monster of a transformer, I think, for how if that 3 amperes is going to your buck converter, that's to supply.
The transformer is only rated at 1 amp, but the magnetic block requires a half an amp. Right now, I measured it at 0.6 amps it's drawing.
0.6 amps.
0.6 amps it's drawing, yes.
And that's only when the magnetic block is being pulled, right?
No, it doesn't matter. It's when it's not.
Draws that all the time?
Yes, it's constant.
Even if nobody's going through the door?
Yes.
The magnetic block is set to be always on.
Yeah.
So you've always got a solenoid drawing power?
Yes.
Okay.
When the valve card reads, the magnetic block is disengaged, so the Pi will send a low signal to the relay that'll shut off the power to the lock.
I think you need to check your rectifier circuit there too.
Okay.
I have main two concerns, which was the original one I addressed last time. When you put such a big magnetic field in a small box with your electronics, that's always you guys see the point of using that, but there are mainly two interferences I'm talking about here. One is the interference between magnetic field and the electronics. The second one is more critical, which is here, which is the interference between the digital side of the system and the analog power side of the system. They can never, if it's a real commercial system, they can never have like a physical current connection, wire connection. You should like auto isolation to separate those two set of things. Like you could prove working once or twice, but the reliability of the overall system is very, very questionable. You understand what I'm saying?
I don't think our we have tested this quite a few times. I have had a lot of issues with that.
No, I know, but still, like if you think about this, you are basically, you have 120 volts goes in, that directly goes to your digital system as well. That's never, that's not very good.
So that is separate. The NFC, so the Pi, the reader, that's separate.
If you look at the wiring, the power, 120 volts goes to, everything is connected. 120 volts goes to the rectifier, goes to the relay, goes directly back to the digital system.
When it goes to the transformer, it's dropped. So the voltage
I know, but
is
still, when you are connected, that's where all the power is. And it's almost like there's So for the entire system, you have one common ground, right? That's my problem.
Yeah.
That's my problem here. When you have 120 volts and the heater system have one common ground, that's a big no-no. You see my point here, right? That's why you can argue whatever you argue about. If you have one system, one circuit with one ground, they interfere with each other. That's the bottom line. And that's almost never, that's actually, and you just like, because those Raspberry Pi all digital systems, those are mini amp systems. And here you have 100 volts goes into that, and it's here one common ground. That's very questionable. And also, like the way you were describing it, if the system constantly draw 0.5 amp, that's very concerning. Because those power, if the relay is not moving, my question is, where does that power go? That power goes into heat. It doesn't go anywhere else. It has to turn into heat. Because we're not doing anything else. Well, then after half an hour, what's going to happen? Do you see my point, David? Because if you're constantly drawing 0.5, you see how many, this is like a light bulb, like how many heat you're going to generate. That power has to go somewhere, right?
Right. Yeah, that's going right into the magnetic block.
Well, that turns into heat, right? If you're not moving.
Well, so the magnetic block requires 12 volts and a half amps, so that is within specification.
I know, but so when the block is not moving, you're not using power, right? You're not, the system is not doing useful work.
So you're using the power until the relays get sent a low signal. That's when the power is shut off to that.
I know, like if, for example, the low-wave touch support for 3 hours, any part of the system using power? The answer is no, right? If any part of your system is not using power, where does that power go? You see my point? Like at that 0.5 amp, where does it go? It has to go to heat, right? I mean, where else can it go?
Like I said before, the lock is receiving that until a valid part hits the reader. So like it just continuously goes into the lock. The lock has to receive that and stay engaged. If it doesn't, the lock is not engaged.
I know, but do you see my point, right? Because if nobody is opening the door, you're not doing useful work. That's a fact. Right? If you're not doing useful work, where does that power go?
Okay.
Right? I mean, only like the work is like one form into another form. If you're not doing useful work, it's turning into wasteful work, and it's turning into heat. That's the only way it can go. So somewhere you can get plugged for sure, the way it's being designed right now.
Follow up with this question. Could you choose a different type of magnetic lock that just needs to be activated when you need to open that? Otherwise, it's just mechanically locked, using a spring or something?
No, it's
So it doesn't draw power for like 10 hours, like overnight when nobody's just using
I'm sorry, can you please repeat that?
it. Like the door.
Yes.
If overnight nobody's using the car, the magnetic lock draws power because it has to kind of keep the door shut.
Yes, that's correct.
Could you choose a different type of lock that only draws power to open it? When it's closed, it's just mechanically closed.
You would have to get a different version.
That's what I'm asking.
Yeah.
Would it be more expensive or just different lock?
It would just be a different stuff, I believe.
So that's the lock that is like overnight. If the solenoid is drawing power, 12 volts, half an amp, how much is that, like 6 watts? So how many seconds is like 10 hours? I don't know. All of the power converts into heat. So you're going to have it heated off like solenoids where there's a damage to wiring,